Newton's three laws. So, projectiles, kind of annoying. Projectiles is not on the syllabus, but it's in the exam. And I've said this before, but nobody listens to me. So it's not in the syllabus, but it's in the exam, so you have to study it. And as you can see, it's actually a big topic. It took us a few classes to do.
So this is the hardest.
First, there's two topics that students find very hard in mechanics. Projectiles is one, and then turning forces is the other one. You know turning force? We'll do that later. These are the two that students find most difficult. Torque, yeah. I don't know why. That's just what they tell me. They find these two the hardest. I think you can maybe understand why the projectiles is difficult. I don't think the projectiles are too difficult. Oh, I was going to print the notes for you. I'll have to do that for Friday then. Right, Newton's three laws. What's up? What about maths?
What did you get? He told me.
For what?
Maths.
We had maths.
Oh, yesterday.
Yeah.
So how much did you get?
That's personal information.
That's correct.
Do you know I can just simply ask the teacher and she'll tell me?
I will sue you.
You can.
I'll do it that way then. Okay, fine. Yeah.
Thank you.
Okay. Newton's three laws then.
At least you won't have to see my thing.
Okay, fine.
Which is bad.
So he's got how much? Okay, right. Newton's three laws. You got that? Yeah. So if you want to be famous in physics, you must have at least three laws, okay? So there's a couple of people. Newton has three laws. Kepler has three laws. Kirchhoff has two laws. So it's not as famous. He's not as famous as Newton or Kepler. Right. So of course, three laws. Let's look at them one at a time. In fact, some of you might even know these laws already. What's Newton's first law? Does anyone know it?
I don't know the numbers, I know.
Yeah, okay. Does anyone know what his first one is?
Maybe it's what you go, nothing will stop you.
Yeah.
Nothing will stop you until you have an outer force.
External force.
Yeah, if a body is at rest, if it's at rest if a body is at rest, it remains at rest. Or if it's in motion, a constant motion, it moves at uniform velocity until acted on by a resultant force. So in other words, simply put, if this is at rest, it will stay at rest unless there's a force. And if this is moving at a constant speed, it will stay moving at a constant speed unless there's a force on it. Now, the first part, if it's at rest, it stays at rest. You believe that. But tell me, if there's something moving at a constant speed in our day-to-day life, it will stop. Even though it doesn't look like there's a force acting on it. But there is a force acting on it.
Gravity,
not gravity, no, because air resistance, yeah. So this doesn't move at a constant speed because the air is acting on it. But if it was in space, it would keep going until it crashes into something, or some gravity force pulls it in.
Yeah, but yes, in the way I have learned, in it there is written in an isolated state.
Isolated, yeah, that's the key words here. I don't want to get too technical, but you're right, in an isolated sort of vacuum.
Yeah.
We're doing Newton's three laws.
The first law, second law, third law.
Yes. But do you know each of them?
Yes, but this is but I do not remember
The
We
numbers.
know.
He said the same thing.
He remembers the name.
Yes.
First floor, second
So
They're there.
Well, like I said, if you get 3, you're famous then. In the exam, they do expect you to remember the numbers, as in which is the first, which is the second, which is the third. So the question could say, what is the first law, Newton's first law? Yeah.
How many laws do you have? 1
Uh,
or 2?
Me, personally, I don't have many. But for the exam, Newton and Kirchhoff are the 2 really that they ask you for. Sometimes Kepler. But if there's going to be a question, it's going to be about Newton. What is Newton's first, second, or third law? Okay, continue.
Yeah.
Right, so here is an example that you don't need to draw this, but it really illustrates the first law. So an object at rest will remain at rest. So as you can see, the ball will just stay put, no moving, unless acted on by an unbalanced or net force. So the ball now moves because there's a force acting on it, and it will move at a constant speed, constant motion, unless acted on by a force. So in this case, the football net is the force here. So this is a nice example I found online that shows you Newton's first law, the 2 parts to it. It stays at rest unless there's a force acting on it, and it will move at a constant motion unless a force acts on it. Okay, so are we all happy with Newton's first law then? Yes? Okay. Right, so now on to the second law, Newton's second law. Now, Adnan, do you want to try this one?
It's I think
You think you have it, Mir?
acceleration-
It's the acceleration one, yeah.
In this law, acceleration is
So-
considered.
Yeah. It is the acceleration one.
It stays at constant.
No, that's the first one which you missed, yeah.
I
So that was the
remember
first
when I
one.
was-
I think that's proportional force.
Yes, it's the one with the force in it, yeah. English. Right, Newton's second law. The simplest way to put Newton's second law is that force is the product of mass and acceleration. You know Newton's second law, we did it a few days ago. F equals ma. Oh yeah, F equals ma. That's Newton's second law. Yeah. Product means multiply. Okay. F equals ma. That is the simplest way to state Newton's second law. Not 100%. It'll do for the exam and the course, but technically there's another version of the law which we'll look at in the next class that's actually more like the original. Okay, so that's Newton's second law. So here's my picture. Force is a product of mass and acceleration. Maybe I should have had acceleration in the picture. But anyway, if it's a bigger mass, you need more force. And if you want more change in velocity, then you need again more force as well. So force is a multiplication of mass and acceleration. Newton's third law. There's only one left, so not gravity.
For every
For every action,
That's it. For every action, there is an equal and opposite reaction. Now that's easy to say. That is easy to say, but actually it's sometimes difficult to understand what the reaction is for the action. And I'll give some examples. The calculator on the table.
Like we throw the ball to the wall and it comes back.
That's one. In fact, it takes many different forms. I don't know if my grammar is right here. I don't know if I should really say for every action there's an equal but opposite reaction.
Equal and opposite.
Equal and opposite?
Same, I think.
Yeah, okay. I think my physics teacher said equal but opposite. I think both are fine. Okay, can I go on?
Yeah.
One second. You did these in high school, didn't you?
Yeah.
Yeah.
Andy?
Yeah.
Okay. Continue.
Yeah.
So here's a nice example that I like. When the air comes out the back of the balloon, that's the action. The reaction is the balloon is pushed forward. That's one example. But there's so many examples. Another example, if I got one here. If the calculator is on the table, there's a weight force going down. But why does it not move down? Because there must be a reaction from the table to cancel it. If I have it here, the weight will make it fall. If I have it here, there's still the weight, but it's not falling. Then there must be a reaction force that balances it. Yeah. The same goes for when you push against the wall. So if I push this, the calculator moves. If I push the wall doesn't move. The wall is pushing me. So this gives us the idea of what's called the reaction force. The reaction force is the force provided by the reacting object. So in other words, the reaction force is what the wall does to me, or what the table does to the calculator. You all know your internet memes?
What?
Internet memes?
What? Not really.
You don't know your internet memes? I touch.
Some.
You know some of them.
Internet memes.
Yeah.
What? Internet means.
What internet memes?
MEMS.
MEMES.
Yeah, I know.
Yeah. Do you know the Soviet Russia one? You know, like for example, in Soviet Russia, Wally finds you. Or
No.
you don't know these? Alright, fine. Then my joke won't work on you. So.
Sorry.
Yeah, that's okay. Yeah. There's an internet meme where everything is reversed. So like it would say in Soviet Russia, hamburger eats you, and there'd be a picture of a giant hamburger eating a person or something. No, you don't know this one?
No.
Okay. So the joke that the student made last year is in Soviet Russia, wall pushes you, which is why it's titled this. But of course you don't know this meme, so it doesn't matter. Yeah, maybe, I don't know. Memes aren't popular anymore.
They are,
Yeah.
but
I have heard like
we're
not for
disconnected.
not this one. Like
Not
there
this
are-
one. Okay. If you type it in, you'll find them. Soviet Russia. Continue?
Yeah.
Yep. Okay. Come on. Stuck. I think it might be stuck because the next one might be a large picture. Come on. Oh, come on. There we go. Wait, that wasn't a large picture. Okay, fine. Right, so here is an example question. Did you find some?
Yeah.
Okay, fine. A block of mass 20 kilograms is on rest at a table. What is the reaction force? Okay, we can just draw this one.
20 Newton.
No, not quite. So let's have a look. Here's our first example here. So we have our block on the table. Oops, on the table. So this is 20 kilograms. So what's the weight here? Do you remember the formula? Weight equals mg.
Oh,
mg.
yeah.
So here this is 20 g. About 198 newtons or something. But this is not moving because there's a reaction force that acts up from the table.
Also.
Yeah. And because it's not moving, they must be perfectly balanced. So we get or must equal 20g as well. So here, that's 20 times 9.81, 196.2 newtons. Now, please listen carefully to what I'm about to say. Please listen carefully. Imagine that the table snapped, and then this starts to slowly move down. Now it's no longer balanced, because if it's moving downwards, it must mean that the reaction is less than this one. And then think about this one. If I grab this side of the table, and then maybe Andy grabs the other side, and we lift the table up, so the table starts to move up, then it's no longer balanced. if the block is moving up in the air because it's on the table, then the ore would be bigger than the 20G. Okay, and that's sometimes difficult to picture. We can all imagine the ore being smaller than 20G because then that means it's falling down.
Yeah.
But if I start moving the table up, it actually means that the ore is going to be bigger than 20G. Okay, right? Please write or draw this example then. So in this example, it's simply to just find ore.
We'll multiply the G by 9.8.
20 times 9.81.
Yeah.
Okay, you drew this? No. Yeah. Continue?
Yeah.
Yeah, okay, great. Right. Okay, now here's another one. A block of mass 200 kilograms is on the table again. A man tries to lift the block up by using a rope, and he uses a force of 1,000 newtons, but the block doesn't move. Okay, so again, we'll just draw this one, and you can try and answer it. So in this example here, we have our block. What did I say? How big did I say it was? 200 kilograms. Yeah, 200 kilograms. And there's a rope here. You know what a man looks like. And he tries to lift the block up with a force of, what did I say, 1,000 newtons. And the block doesn't move, he's not strong enough, because the weight here is going to be like 2,000 newtons, okay? So first, I just wanted to draw this. This is the question. Well, actually, let me draw in all the forces. So what's this force down here? This in 200G, yeah, this is the weight. And I'm missing a force. What force am I missing here? I haven't actually drawn the reaction force from the table, because this is not the reaction force. What force is this? From the man, the pulling force. Yeah, okay. So please draw this, and then we'll have a look.
Why you are writing 200G instead of kg?
No, that G is 9.81G, not gram G. You're not the first person to make that mistake, and you won't be the last.
Oh.
This is the problem using the same letter for grams as for gravity. Yeah.
Gravity.
Yes, not grams, yeah. Okay, continue. Right. So in this example, the ore is not 200G. It's not moving, but the ore doesn't equal 200G. Do we know what?
1,000, because it's already falling to 1,000.
Not quite. We can say that ore plus 1,000 equals 200G. It's still balanced, but the result is the ore will be smaller now when we take this over. So 200 times 9.81 minus 1,000 newtons. So then that means we get an ore of 962 newtons then. Okay, write that down. Are we getting the idea of reaction force? Yeah.
So how do we get magnitude again?
200 G minus 1000. I just hit it in on the calculator. It's going to be, I typed this in, 200 times 9.81 minus 1000. Okay, is that okay? Continue? Right. Now we're getting interesting. I don't need you to write all this down. There's a lot of English here and your English is quite good. But what I want you to do is to read it and to draw it. That's all. Read and draw. Let's see what you drew. Very good, that's right, yeah. Yeah, you just left out one force on your diagram.
Yeah, the jar.
Yeah, oh yeah, just draw that in too. Yeah, and just draw in the forces as well, actually. Okay, Andy, can I see what you drew? Not quite. What is, look, have a look at Andy's and tell me what he missed. The angle. Yeah.
Keep your head up.
The man needs to be pulling a bit higher, yeah. Okay, so what happens here,
It's 2000 kilograms.
this is 2000, is it?
200.
200 kilograms. And the man is pulling at an angle of 45. So, let me just, I don't know, I'll just put it here in the center. That's 45 degrees. And his force is 1000 newtons. And of course, there's your weight. That will be 200 G. And there's a reaction force here.
Yeah.
Now, in this case, we have to resolve his force. This will be 1000 cos 45, and this one here will be 1000 sine 45. And the question is, what is the reaction force? So what equation can we make here? What equation should we make here? We should say or plus 1000 sine 45 equals 200 G. Because this vertical here must cancel this vertical. Because if it didn't, then the block would move off the table. Is there anything to cancel this on the left?
Yeah, pretty.
Yeah, but there's no friction in this one. Usually, yeah, but in this example, no. So would the block move horizontally? Yes.
Yeah.
Because there's nothing to cancel this, when the man pulls on it, it will move to the right. It won't move up because this will cancel it, but it will move to the right because there's nothing here to balance it. Do you know what I mean? Yeah. Well, anyways, we don't worry about that just yet. We're just looking at the vertical. So here we can get or equals 200 G minus 1000 sine 45. So if I hit that in on the calculator, I get 1255 newtons is the or. Okay, so if you can write this down. Yep. You can't see? Do I need to move?
125.
Oh, this is a little blurry. Why didn't you say anything?
No.
Yeah? We're good to continue? Okay. So next now. 2 more questions. Right. Again, I want you to read and draw. You drew it?
Yeah.
It's nearly the same, except for one difference. What's the difference?
This is what that's what
That, yeah, and what else? A big difference? Friction force.
Yeah.
Friction force from the table. So, here, yeah, so in this one, let's draw it. Okay, so what's the mass of the block? 73 kilograms, yeah, so the weight here is 73 G, and of course there's the reaction here. And once again, our man is pulling at 45 degrees, 1000. So I don't really want to write it in because I don't care about that. What I care about is the horizontal, which will be 1000 cos 45, and the vertical, which will be 1000 sine 45. And now there's also this friction force. So we have R plus 1000 sine 45 equals 73 G, and the R equals typing this in, we get R equals only 9.02 newtons. Yeah. That's the first part. The second part is they want the friction. Now, listen very carefully. The block is moving to the right. See in the question? The block is moving at a constant speed. It's moving to the right. So it's going along this way. So, will 1000 cos 45 equal the friction? Yes or no?
No. It will be minus.
No.
The answer is yes. Because of the key word.
Constant?
Constant. Remember, there's only a force if it's accelerating. But Newton's first law says if it's moving at a constant speed, there's no force. Do you remember? The first law. If it's at rest, it'll stay at rest until there's a force. And if it's at constant speed, it will stay at constant speed unless there's a force. So because it's moving at constant speed, there is no force.
It's basically the same as the thrust and drag, right?
Yeah.
No
yeah.
acceleration, no force.
Yeah. Yeah.
But why is it more?
Huh? Yeah, yeah.
They cancel each other, maybe?
This force cancels this force. So it's not accelerating, but it can still move at a constant speed. So what happened is something put it in motion. You know, like for example, if I tap this, well, maybe if I tap it, it still moves even though I'm not touching it. And the only reason it stops is the force from the table. But if there was no table and I tap it, it will just keep moving. Yeah. So this cancels this because it's moving at constant speed, and Newton tells us that it means there's no force in total on it. So this must cancel this. Yeah. Okay. So that just means friction is equal to 1000 cos 45. $707. Now, if the question said, as the man is pulling the block and the man is accelerating, then you don't know. You don't know because you just know that 1000 cos 45 will be more than the friction. There'll be a net force causing an acceleration. So it's because the question said constant speed is what makes it solvable. Okay. Next.
How do I get the friction?
The friction equals this. Yeah? Okay. Is that okay, Andy?
Yeah.
Right, we have one more example to do. Do I have another homework to do, or was it just projectiles?
There's one more.
There wasn't anything with weight.
No.
No, okay, good. Right, so again, you can just read and draw it if you want to. You all know what a weighing scale is? Weighing scales is what you stand on to get your weight in basket. Yeah.
Kilograms.
Says it in kilograms, yeah.
Some mass.
Yeah, but really what I'm saying in the story is the weighing scale doesn't measure your mass, it actually measures your weight and it converts it into kilograms, but it actually measures the force. So for example, if you jump on the weighing scales, it'll jump up, but that doesn't mean you have more mass. Does it mean you're fatter? No, it doesn't. So it's not really measuring your mass, it's measuring your weight and it's converting it into kilograms. But technically speaking, it should really give your weight in newtons because it's measuring a force. Yeah?
Like this.
Yeah, like, I mean, it's not really measuring your kilogram mass. Anyways, a weighing scale really measures the reaction force rather than the weight as well. So in this little story, what happens is you have your weighing scales, and what's happening is that there's, what did they say, 1 kilogram? No, half a kilogram. Half a kilogram book. Okay, so there's a book here, and it's 0.5 kilograms. Now, your weighing scales in your bathroom will say 0.5 kilograms on it, won't it? But really, if it's a weighing scales measuring weight, it should say it in newtons. So let's pretend we have a physics weighing scales and it says it in newtons. Okay. So what's the weight? The formula for weight is mg. So in this case, it should really say 0.5 times 9.81. So the screen should say 4.905 newtons. That's what it should say. Okay, is that okay so far? Alright, so I'll just clear the screen. Beep. Now, what is the weighing scales measuring? You might think to say, oh, it's measuring this W force. It's not. It's measuring the reaction force.
Yeah.
Now that doesn't matter if it's not moving, because if it's not moving, W is the same as R, so it doesn't matter. Okay, but technically the weighing scale is measuring the reaction force, not the weight. So it should really be called a reaction scale. Yeah. Because it's measuring how much it's pushing on the block, you know. It's not measuring the weight, it's measuring how much it's pushed against the block. So it doesn't measure how much my hand is pushing, it's measuring how much it is pushing back. Yeah. Anyways, there is a weight here of 0.5 g, and if it's not moving, or equals 0.5 g. Yeah. Now it gets interesting if it is moving. So if I put this in an elevator and the elevator moves up, so that there's an acceleration of 1 meter per second squared, let's see what happens. Is it balanced now? No. There's a total force going up. Yeah. Newton says F equals ma. What is the F here?
Same, 0.5.
No.
Force.
Yes.
Multiplied by
No.
1.
Or
No.
minus 0.5.
Yes. Or minus 0.5 g. Because the or will be bigger than this because it's moving up. So the total force, because remember F is total force, will be this one minus this one. Remember we said F is total force?
Yes.
Okay. What's the M? 0.5. And the A is 1. So I get or equals 0.5 plus 0.5 g. So the or is 5.405 newtons. Now remember, what did I say it should say if it's not moving? We said at the start it should say 5.905 newtons. Will it say that now? No. Instead it will say 5.405. So the elevator makes the weighing scales think and feel like the object is heavier because as it's moving up it's getting pushed into it more. How much more? Let's calculate as a percent. So this, if you convert it into a percentage, this is an extra 10.2%, the difference. So if the weighing scale thinks it has a 0.5 kilogram mass on it, but it doesn't, it's put into an elevator, instead it will think the mass is an extra 10%, 0.55 kilograms. So if you were to do this experiment, if you were to put the 0.5 kilogram book on the weighing scale, it will say 0.5 kilograms. You put in an elevator, and what will happen? It will go up to 0.55. And then when the elevator stops, it'll go back to 0.5. Then what if the elevator goes down? It will decrease to, what do you think?
10%.
Yeah, again, about 10%, 0.45. Okay, so this question is maybe a little bit too difficult for the exam, but I like it because it really gets you to understand exactly what's happening with reaction force here, okay? So if you can write this one down, and then we'll have a look at the homework here. This one, being honest, it's a tricky one to think about, okay? But, you know, thinking about the difficult questions is what makes you a better student and get better. If all the questions are easy, then you're not really learning anything. Yeah. Okay, did you write this down? Yeah, you have all this? Good. What would happen if somebody cuts the elevator cable and the elevator is falling?
Zero.
It would say 0. Yeah.
You would die.
Yeah, but you will see that it says 0 before you die. So before you die, you can think, you know, Stephen was right. It does say 0 kilograms on it.
That's the way to die.
That's it, yeah. By the way, if you do find yourself in a fallen elevator, which is very unlikely.
I'll jump before sitting.
Nope.
Why not?
Do you know the best position to be in when the elevator hits the ground? No.
In the bottom, like in the corner.
No.
Sit
No.
down, follow it.
No.
What is it?
Yeah, the best position to be in is you want to lie on the ground, believe it or not.
Yeah, because when it hits, I will not hit the ground and die. I will already be.
You'll already be on the ground, number one, and also later we'll talk about pressure.
The lift will.
Pressure is force over area. If you make the area bigger, It's less pressure. And also, the other thing is, when the elevator hits the ground, if you're standing, all of the force goes up your legs. Remember the example we did with the man jumping off the ground? This will likely break the bones in your legs. But if you're lying on the ground, the force, instead of going through the leg, it will go perpendicular to the leg. It's less likely to break the bone then.
What if I jump?
No, that
But will
No.
it make it lift?
it will not.
It will.
It will not.
Why won't it?
It will do absolutely nothing.
No, okay, the lift is already moving. I
Yeah.
understand the lift, so I'm moving at the same speed. What if I jump, the speed is going to be less, like the speed of going down?
Yeah, but you still, after you jump, you still have to fall back to the ground. You're
Yeah,
not
but
going to jump.
Like the small jump is going to save.
No, think about this.
I know what you mean.
No, watch, right, okay? If you're falling, there you are in the elevator, okay, and if you're falling, and imagine when the elevator hits the ground, you have jumped up in the air.
Okay, I will fall,
But you'll fall back down.
Yeah, but I will.
And the speed you will hit the ground at,
Same as the elevator.
it's the not only is it the speed of the elevator, but it'll also be the speed plus what you gave yourself to go upwards. So if you jumped up at 1 meter per second and the elevator's fallen at 20 meters per second, you've made the situation worse. You will now hit the ground at 21 meters per second.
No, but I thought it was supposed to be 19. So
When you hit the ground, when the elevator hits the ground, you will be moving up in the air with 19. Oh, I'm sorry, you're right. I got it wrong. I'm so sorry. Yes, you will hit the ground at 19.
I feel so smart right now.
Yeah, but I mean, look at the number you're saying here.
Yeah.
Instead of hitting the ground at 20, you'll hit it at 90.
Technically, I should feel smart. Technically, yes.
If that will help you sleep at night,
Yeah.
yes, okay. Yeah.
I've actually read a story about a girl jumping on the elevator.
No, this sounds so made up. I would not believe this for a moment, because this has actually never happened. There's never been a case of the elevator collapsing to hit the ground, because the elevator has little brakes in it that clamp onto the wall if it starts to fall.
And,
Yeah.
and it also like takes twice as much as it says usually.
Exactly, yeah.
There was a elevator in my country, and like five people went down, and they were like this much. It was fall down, 3 were died.
Really?
Yeah.
Okay, I'll have to look this up anyway.
So like, they all were like, they were saying that maximum like, yes, there was written that maximum that this much kg should be, people should be there.
Okay.
They were 5 like 10, they were like 10. It was so, it was not a
I'll Google this.
Yeah.
Okay, I don't know if you want to take a picture of this then, so this is the homework then.
Tomorrow is class? Friday.
Yes.
Yes. Tomorrow is sequel.
I need to think
Me too.
all day.
We
During
don't
the
have anything
presentation
tomorrow,
and
do
this.
we?
Yeah.
Well, I'll do the chemistry work we can.
Okay,
I'll
we'll
do the bus.
Physics and chemistry.
continue then.